Hi everyone. Today we are discussing about convolution and LTI systems. Today we are discussing about convolution and LTI systems. In this first topic is impulse response. Impulse response. The speech signal H of a system, capital H, to the input delta is called impulse response of system. That means small h is equal to the function of delta, that is a impulse response of the signal. Impulse response of the signal. For any LTI system with input x and output y, for any LTI system, LTI means linear time invariant systems. Linear time invariant systems. For any LTI system with x input and y output, and the impulse response h of the signal is related x and input and output, and impulse response function h is represents the output y equal to x into h. The output y equal to x into h. That means the output signal will be depends both x and impulse response of h. That means y equal to x into h. In other words, a LTI system simply computes a convolution. Computes a convolution. Computes a convolution. Furthermore, LTI system is completely characterized by its impulse response. Completely characterized by its impulse response. Compute convolution means it will change the rate of the signals with time and amplitude. That is, if the impulse response of a LTI system is known, we can determine the response of the system to any input. That means response means how many input signals are entering to the input side, and what type of signals are received from output side. So that variation will be depends on LTI system. In LTI system is also characterized or categorized. LTI system is also used to categorize or calculated to determine the process response of the LTI system to any input. For example, when I am input side applying several inputs and output side getting several outputs, that means y will depends on x, and it will determine some responses of the system signals with respect to the input. That is the meaning of determining the process of the system to any input. Since the impulse response of a LTI system is an extremely useful quantity, we often want to determine this quantity in a practical setting. In a practical setting. And last point, unfortunately, in practice, the impulse response of system cannot be determined directly from the definition of the impulse response, and it will faces some problems with respect to the practical terms. And next topic is step response. Step response. In previous classes, already we are discussing how to convert these signals from one form to another form. For example, a continuous time signal will be converted is in the form of sampling signals, and then after the sampling signals are converted is in the form of the sampling signals are converted is in the form of digital signals. That means by using step responses, it will explain how to convert these signals, how to behave the signals to convert in different forms. That is the brief explanation of step response. In the process of analog to digital conversion, we are using sampling or quantized pulses to divide the signals to the equal intervals. So in equal intervals it will divide equal step sizes. Now we are discussing step responses. The response of step S, the response S of a system H to the input U is called the step response of system. That means S equal to H of U. That means step size of the function will be depends on the input signal U. The step size of the function will be depends S equal to H of U. The impulse response H and step response S of a system are related as H of t equal to differentiate of step size of t with respect to the dt, and that means the rate of change of step size with respect to the time will be depends on dt, differential signals. Therefore the impulse response of a system can each determined from its step response by differentiation. The impulse response of a system can be determined from its step responses by differentiation. That means the overall concept of step size will be depends on to the conversion differentiation rate of d by dt of s of t, where s of t is the step size of the signals with respect to the time. So that means step size will be depends on response by the differentiation. Step sizes will be depends on differentiation. That means step sizes are depends on differentiation. Step sizes are depends on step sizes and differentiation functions. And step size response provide a practical means for determining the impulse response of a system. That means it will clearly explain how to convert the step sizes from various functions, and in this topic we can easily explain how to convert the signals from one form to another form or different step sizes with the help of the function h of t or formula h of t equal to, where h of t is the system function, s of t is the step size function, d by dt is the rate of change of differentiation of data signal. Next one is block diagram representation of LTI system. Block diagram representation of LTI system. Often it is convenient to represents a continuous LTI system in block diagram. Since such systems are completely characterized by their impulse response, we are often label a system with its impulse response. That is, it represents a system with X input, Y output, and impulse response H, as shown in the below. Here, X of t is the input signals and Y of t is the output signals. X of t is the input signal and Y of t is the output signal. H of t is the impulse response function. Impulse response function. That means the output signal Y of t. That means the output signal Y of t will be depends on X of t. The output signal Y of t will be depends on X of t. Next topic is interconnection of LTI systems. One of the important topic, interconnection of LTI systems, linear time invariant systems. In the series interconnection of LTI system with impulse responses H1 and H2, in the LTI system with impulse responses H equal to H1 into H2, that is, we have the equivalence shown below. And these are the related example diagrams of interconnection of LTI systems. Here we are seeing H1 and H2 equal to H1 and H2 Y of t. X of t equal to H1 and H2 t dt. X of t equal to H1 and H2 Y of t. That means when we are using two techniques, one is H1 into H2 technique, second one is input equal to output. Series, that means it is connecting serially to the functions of H1 and H2 or H2 or H1. That means A into B or B into A. A into B or B into A. That's why we are indicating H1 of T, H2 of T is replaced H2 of T and H1 of T. That means we can change the functions from starting to ending or ending to starting with respect to the input and output signals. Next one is parallel LTI interconnection systems for the LTI impulse response, and it is also connected the functions H1 and H2 parallelly. These are the circuit diagrams of parallel LTI system. In parallel LTI system, the function H1 and H2, the function H1 and H2 are connected. The function H1 and H2 are connected parallelly with the help of adder. It will receive both function 1 and function 2 signals. It will receive both function 1 and function signals, and the final function or final signal is propagates through the H1 of t plus H2 of t. h1 of t plus h2 of t, h1 of t plus h2 of t, h1 of t and h2 of t is connected by the adder. That's why the output function is represents x of t equal to h1 of t plus h2 of t. That means in this we are using adder function, which is helpful to adding the individual functions or individual systems, LTI systems, h1 of t and h2 of t, h1 of t and h2 of t. In h1 and h2 are passing through the adder. So by using adder we can easily adding the signals. By using adder we can easily adding the signals with respect to the y of t. By using h1 of t and h2 of t, we can get the output signals from the output side y of t. And by using serial and parallel interaction of LTI systems, we can easily adding, multiplying and exchanging the signals or functions with respect to the input and output signals and time. Next topic is properties of LTI systems. A LTI system with impulse response H is memoryless if and only if h of t equal to 0 for all t not equal to 0, h of t equal to 0 for all t not equal to 0. That is, a LTI system is memoryless and only if it considers impulse response. H is the form h of t equal to k into delta of t, where k is the complex constant, where k is the complex constant. A LTI system is memoryless. That means they are not internally used. They are not internally used memory device or memory portal or memory element. Already in previous class we know parallel and serial data circuit arrangements and function arrangements of impulse response of LTI systems. In LTI systems already we are seeing series and parallel. Already we are seeing series and parallel. In series and parallel only we are using input signals and output signals. Only we are using input signals and output signals and does not use memory device or feedback network or memory and data device. That's why LTI system is a memoryless device. Why? Because it is not using memory device internally. That's why it is only interconnection networks and they have no way to store the information. Why? Because memory elements are not arranged on the particular devices. So that's why we are seeing second point, that is a LTI system is memoryless. A LTI system is memoryless if and only if its impulse response H is H is of the form. H is of the form. That means H is a function where h of t equal to k into delta of t, where k is the complex constant. complex signals, mixed signals, where H is the complex constant. Next, consequently, every memoryless LTI system with input X and output Y is characterized by an equation of form sorry an equation of form characterized by an equation of form y equal to x into k delta equal to kx, where the system is an ideal amplifier, and then automatically we can eliminate the delta term delta. So if the system is used ideal amplifiers at the situation we can eliminate the term of ideal term of delta. Why? Because internally we are using ideal amplifiers at the situation, we can neglect or eliminate the delta. For a LTI system, the memoryless constraint is extremely restrictive, as every memoryless LTI system is an ideal amplifier. But in LTI system, use ideal amplifiers, which is more helpful to conversion of data signals from one form to another form, And next topic is causality. A LTI system with impulse responses H is causal if means H of t equal to 0 for all t equal to less than 0 conditions. T less than 0 conditions. H of t, that means the function H of t equal to 0 where for all t less than or equal to 0. A LTI system H of t equal to 0 for all t less than 0. H is a causal signal. It is due to above relationship that we call a signal X satisfying x of t equal to 0 for all t less than or equal to t less than or equal to satisfying x of t equal to 0 for all t less than 0, a causal signal. Next one is invertibility. The inverse of a LTI system, if such a system exists a LTI system, let H and H inverse denotes the impulse response of a LTI system and its LTI inverse respectively, then H into H inverse is equal to delta. H into H inverse is equal to delta. Consequently, a LTI system with impulse response H is invertible and the function of invertibility H into H inverse is equal to delta. Consequently, a system with impulse response H is notable, and if only if there exists a function H inverse such that H into H inverse is equal to delta. Except except in simple cases, above condition is often quite difficult to test. Next one is Bibo stability. One of the important topic, Bibo stability. Bibo stability means bit input, bit output. Bit in, bit out. Bit in, bit out. That means how many input signals are entering to the system and how many output signals are outgoing from the output side. And these are all responsible by using Bibo stability, which is explain the total number of signals will be propagates from output side and how many signals are entering from input side. That means it is like a calculator which calculate the number of input and output signals. A LTI system with impulse response H is Bibo stable if and only if, and that means the Bibo stability function integration of infinite minus infinity to infinity mod h of t dt where less than or equal to infinity. This is the condition of Bibo stability. Which is more helpful to calculate the input and output signal transmissions with the help of the formula integration of minus infinity to infinity h of mod h of t dt less than infinity, where h is absolutely integrable, where h is absolutely integrable, where h is absolutely integrable. Next one is eigenfunctions of systems. Eigenfunctions of systems. Eigenfunctions of systems. An input x to a system H is said to be eigenfunction of system H with the eigenvalue lambda is corresponding output. Y is the form y is equal to lambda x. Y is lambda x, where y is the output function of the eigensystems and x is the input signals of system H and lambda is the complex constant. So eigenvalues represents the wavelength values with respect to the lambda, and in other words a system H acts an ideal amplifier for each its eigenfunctions x, where the amplifier gain is given by the corresponding eigenvalue lambda. Different systems have different eigenfunctions. Eigenfunctions means it is different signals compared to the different functions compared to the other functions of a particular interest or the eigenfunctions of LTI systems. LDI systems. Eigenfunctions of LDI systems. Eigenfunctions of LDI systems. Eigenfunctions of LDI systems. As it turns out, every complex exponential is an eigenfunction of all LTI systems. Eigenfunction of all LTI systems. It turns out every complex exponential is an eigenfunction for all LTI systems. Complex exponential function, that means lambda value. Complex exponential function is an example of eigenvalues or eigenfunctions, and which is represents lambda, that is LTI system of h of t impulse response h is e of st is equal to h of s of est, where s is a complex constant, where x is a complex constant, and e power st is eigenfunction of LTI system, and h of s is the corresponding eigenvalue or function. Corresponding eigenvalue or h. H of s is equal to integration of minus infinity to infinity h of t e power minus st dt. We refer to h as the system function or transfer function of the h. Just we are observing the capital H and small h. These are the different system functions and transfer functions. Different functions and transfer functions of h. From above, we can see that the response of LTI system to a complex. Next one is representation of signals using eigenfunctions. Consider a LTI system with input x and output y and system functions h. Suppose that the x input and expressed the linear combination of complex exponential x of t equal to sigma of k a of k e power s skt and where the ak and sk are the complex constants, where ak and sk are the complex constants. Using the fact the complex exponentials are eigenfunctions of LTI system, and we can conclude y of t equal to sigma of k a of k h of sk e of e power skt. Thus, if an input of a LTI system, or if an input to a LTI system can be expressed as a linear combination of complex exponentials, the output can also expressed as a linear combination of the same complex exponential. Thus, if an input to a LTI system can be expressed as a linear combination of complex exponentials or complex exponentials. The function, the output can also expressed used as a linear combination of same complex exponential. So that means in LTI systems we are using both complex linear and exponential functions to convert the signals in different forms. Next one is continuous Fourier series, CTFS. Continuous Fourier series, continuous time Fourier series, continuous time Fourier series. Introduction. The Fourier series is a representation of periodic signals. The Fourier series is a, that means Fourier series is a x1 x2 x3 up to x of n. That means um, the scientist Fourier, it is a name of scientist who invented the Fourier series signals and Fourier series equipments or Fourier series exponential series, which is more helpful to our real life by using Fourier series, and we can easily execute the use of Fourier series through the uh, future and upcoming, and today onwards we are all using Fourier series information to the different conversion techniques. Actually, Fourier is a name who invented the series. That's why it is called Fourier series. Fourier series. The Fourier series is a representation for periodic signals. The Fourier series, a signal is represents a linear combination of complex sinusoids. Linear combination of complex sinusoids. The use of complex sinusoids is desirable due to their numerous attractive properties. The use of complex sinusoids is desirable due to their numerous attractive properties. For example, complex sinusoids are complex sinusoids are continuous and differentiable. They are also easy to integrate and differentiate. By using Fourier series, signals are mostly used in mathematical expressions to simplifying the signals with the help of integration and differentiation. Perhaps most important complex insights are eigenfunctions of LTI systems. Eigenfunctions of LTI systems. So every Fourier system contains several series numbers or series devices or series numbers, which is to estimating the data transmission to the devices. How much of data will propagates through the LTI system, and how much of information will propagate to the devices, and what are the input and output variables. We can easily understand by using Fourier series, and we can calculate the rate of change of the data transmission with the help of series with the help of Fourier series. Next heading is Fourier series. Fourier series. Harmonically related complex sinusoids. Next topic is harmonically related complex sinusoids. Complex sinusoids. A set of complex sinusoids is said to be harmonically related if there is exists some constants W naught such that the fundamental frequency of each complex sinusoid is an integral multiple of W naught. Consider the set of harmonically related complex sinusoids given by pi of k of t equal to e power j omega 0 t for all integral k. The fundamental frequency of the kth complex sinusoids pi of k is k omega 0, an integral multiple of w naught, an integral multiple of w naught. Since the fundamental frequency of each of the harmonically related complex sinusoids an integer multiple of W naught, a linear combination of these complex sinusoids must be periodic. A linear combination of these complex sinusoids must be periodic. More especially, a linear combination of these complex sinusoids periodic time period is 2 pi by W naught, where t is time and pi is angle and W naught is the wavelength of the angle. So time period t equal to 2 pi by W naught. Next topic is CT, continuous time Fourier series. A periodic function signal x with fundamental period t and fundamental frequency omega equal to t by t. That means t equal to 2 pi by omega naught. When we are simplifying omega naught value, omega naught equal to 2 pi by t can be as a linear combination harmonically related complex sinusoids as x of t equal to summation of k equal to minus infinity to infinity ck e power jk omega t. Such a representation is known as complex exponential of form of a continuous time Fourier series and ck are the called Fourier series coefficients. The above formula for x is often referred to as the Fourier series synthesis equation. The term is summation for k equal to k and k equal to minus k are called the kth harmonic components and have the fundamental frequency k omega 0. To denote a signal x has the Fourier series coefficients. Consequence c of k we write. So these are the different functions and different categorization of Fourier series and CT Fourier series. continuous Fourier series. Next class we are discussing more topics which is more helpful to further topics. Thank you.